Caffeine's a good drug, right? Who doesn't like caffeine? So, give me a second. Get this right. So we have nitrogen, other nitrogen. There we go. Caffeine. What is this? I'm sure you've seen chemical symbols before, haven't you? Usually they get a necklace of this. What does this mean? I guess I was trying to make this backwards. I will put the original one so it doesn't confuse y'all as all the... I wanted to get it slightly different. Let me draw it like this, how it was originally done. So I can actually saw you. Usually they put it like this. The same way, either way. The mirror images of each other. I just rotated it 180 degrees to the paper. This is caffeine for another point. What is this? Let's look at it more realistically. Does that look the same? So there it is. Same shape. We see the blue nitrogen. So 1, 2, 3, 4. I'll explain this in a little bit. You see the 2 oxygen in red. And anywhere there's an intersection, we see this black. What do you think the black is? So here's an intersection. Then we see at some molecules these white atoms. The carbon and hydrogen. So let's put a pause on this for right now and go over the rules. This is known as the chemical skeletal, correctly. Chemical skeletal structure of an atom or molecule. Let's suppose we have a line segment. This is a molecule. Every endpoint that isn't connected to an atom is a carbon. Every endpoint not connected to an atom is a carbon atom. So we have a carbon here bonded with another carbon. Do y'all remember Lewis dot diagrams? What does every atom except for hydrogen want to have? 8 valence electrons. How many does hydrogen want? So let's add the valence electrons. 1, 1, 2, 3, 4. 1, 2, 3, 4. Carbon has 4. So what we're going to do is to complete the octet rule, we're going to come over here and add in hydrogen to complete the octet rule. So what we end up with is this chemical here. Which is C2, 1, 2, 3, 4, 5, 6, 8, 6. So this is the Lewis dot diagram. This is the molecular formula. And this is the skeletal structure. Yep, that's it. That's all you need to represent it. You have a carbon here, a carbon there, and you need to balance out the carbon's valence electrons by adding hydrogen. This is very useful for organic molecules. Organic molecules is an outdated term. It is suggested that we rename this as carbonic molecules or I forget the term. It's a matter we stick with organic molecules. Organic molecules are molecules that contain a lot of carbon and hydrogen. A lot of carbon. That's all organic molecule. We find it in biology a lot. Almost all the molecules that we have are carbon-based. We're carbon-based life forms. Sugar has a lot of carbon in it, and so forth. So let's do another example. Let's do this line right here. What would this molecule be? How many carbon does it have? Start there. So every endpoint not connected to an atom is a carbon. 1, 2. This endpoint is connected to an atom. So we have a carbon attached to another carbon, is attached to an oxygen, and hydrogen is attached to that oxygen. Go in and add valence dots around it. There's 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Oxygen has 6. Hydrogen has 1. For every one of the carbons, we need to add hydrogen to complete its octet role. And that's it. Usually we flatten this. So it's like carbon attached to a carbon, attached to oxygen, attached to hydrogen. And we have like that. Usually it's flattened. I don't care on the homework or test. If you flatten it, I will accept both of them. It looks better flattened, but some particles are impossible to flatten. Molecules, I mean. So the formula is C2, 1, 2, 3, 4, 5, 6, and 1 oxygen. Sometimes this is written as C2H5OH to illustrate the structure that we have an OH attached to the C25. But you can put the molecular formula as that, just count how many atoms it is. A very famous chemical that you've heard, no doubt, is benzene. Y'all heard of benzene? And usually when talking about oil and stuff, you'll hear it mentioned, especially benzene toxicity. A very useful chemical, gasoline production, oil production, and such. What did it look like? You'll notice something different. I have an extra line by some lines. What do you think that means? What would you think this extra line next to this other line would be? Where's the endpoint? So an endpoint here, endpoint here, here, input here, input here, input here. Go ahead and this is a carbon. This is a carbon, 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 this carbon. So we have a carbon down here. This double line, a double bond. The single line, single bond. I have enough space. So we have two carbons here, they're double bonded, single bond here, another carbon here that has a double bond, single bond here, double bond here, a line like that. So let's add in our original valence electrons. 1, 2, 3, 4. Carbon has 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. You might notice that every carbon is going to end up with 4 lines around it. Because a line contains 2 electrons. They're being shared. These are covalent bonds. So this is the structure for benzene. We have 1, 2, 3, 4, 5, 6. And each carbon has hydrogen. So this is the chemical formula for benzene. You'll often see benzene written like this. What do you think the circle represents? So, looking at these double bonds, so there could be a double bond between this carbon and that carbon, or the electrons could switch and we have a double bond here. These particles alternate back and forth. The electrons, remember in covalent bonds, electrons are shared between atoms. So some of the time the electrons are around this carbon, some of the time they're around that carbon. And what ends up happening is you get alternating single and double bonds. And what this means, the circle just means it's alternating. You don't need to know this. I don't give y'all any on the homework or test that has the circle. But you do see stuff like this. So I'll just make something up. If you ever see this, where you see two dashed lines, and sometimes this circle is written as a dash circle, it means alternating. This could either be a double bond here and a single bond here, or it could be a single bond here and a double bond here. So if you see two dashed lines like this, it means that the double single bond alternates between these two possible things, and I like to illustrate that. It does have importance as it changes some high level stuff. We don't need to worry about. What will this one look like? One, two, three, four. I like flattening it. You don't have to. You can either do C, bond it with a C, bond it with a C, bond it with a C. But I like flattening it so that it looks like that. How many hydrogen do we need around this carbon? 3. So it has 1, 2, 3, 4 valence around it. So we need to add. How many would be around this carbon? 2. Every carbon is going to have exactly 4 lines. So this is C2. 1, 2, so 4, 8, 10. I'm getting ahead of myself. This is butane. So why is this important? So, for the most part throughout this class, I give you a formula, and you know what the molecule is, right? You can go from a formula to a molecule. So, C5H12O. What molecule does this refer to? Let's look. So here's a list of possible formulas. Are molecules the same? Do they look the same? They're all different. There are actually 25 different molecules. Maybe, I don't know. Some of these could be duplicates. That share that common formula. For normal high school level chemicals that you'll work with, you can usually go from formula to exact molecule. Every molecule has one formula. But once you start going and doing real chemistry, that's no longer true. The base formula is useful in doing molar math and calculations like that, but we can't say what that is. I'm going to see if this has a name. Its name are these numbers. I mean, there is a proper way of naming them, but they're complicated. Like the nomenclature for these chemicals are extremely complicated. Let me click on one. pentanol, that has a unique name. Three methylbutane 1-ol. That's this chemical. I honestly don't know how to go from a name to formula or formula to name. It's a lot of nomenclature memorization. But I want y'all to at least walk away from this class and see someone's necklace that has, or a coffee mug that has a chemical on it, and go and know what that chemical is, or at least what the formula would be, what it means. So, you've never seen a caffeine necklace? Oh my goodness. I've seen like several people wear them. Like these little necklaces. Well, it's that's how the shape is. So let's go back to our caffeine. So what would this be? So we have a carbon attached to a nitrogen attached to a carbon. So a carbon is right here. It's double bonded with an oxygen. So right here, 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 and here, and here. So every endpoint that is not connected to an atom becomes a carbon. Yeah, like that. Go back and add your dots, your valence. So how many does nitrogen have? 5. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I don't care if they're in the middle or outside. 1, 2, 3, 4, 5. So one of the valence electrons are already in this bond. Oxygen has how many? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then you could also do it to all the carbons too, but it's unnecessary because we'll immediately replace them with hydrogen. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So we need to balance it out by sharing an electron from a hydrogen. And you only do it to carbon atoms, none else. Make sense? So how many carbon do we have? Alright, looking at the original. 1, 2, 3, 4, 5, 6, 7, 8. Double check. 1, 2, 3, 4, 5, 6, 7, 8. How many hydrogen do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And nitrogen? Yeah, easier to look back over here. 1, 2, 3, 4. And oxygen. 1, 2. Let's see if we're right. Caffeine formula. So, and I forgot oxygen goes afterward. Oh yeah, I did that. So C8, H10, N4, O2. Making sense? Do some more. Yep. A little note before I move on. So we did this one right here, right? The carbon bonded with a carbon, and we have hydrogen around it. All right. Sometimes they'll do this. Sometimes a CH3, they want to specify it. And this is the only major exception. Except for this one case. So remember in Lewis dot diagrams, what does carbon do? Carbon is always on inside. Hydrogen is always on outside. You don't really need to know this, but the more electronegative is on the inside if it doesn't fall. So first check this, then check this, and more electronegative on in center if it's not carbon or hydrogen. Usually this endpoint here is wherever atom this is going to be. So for example, if I were to have done this, then this represents an oxygen bonded with an oxygen. And then we have a hydrogen bonded with that oxygen and a hydrogen bonded with that oxygen. This is the skeletal structure for hydrogen peroxide. This is the exception I wanted to do, tell you. Because of the rules, we sometimes put whole molecules here. CH3 is a methyl group. CH3. It's a very common thing to show, as this does a lot of chemistry with it. So they'll cheat and abuse the notation slightly. You can either put atoms like this, where the most closest one, but you will occasionally see it like this. This is the same thing as that and this. There's no exceptions. I'm not going to give you anything like this. You should always bond it like this. The reason why is this is optional, and I will come in and manually remove it whenever I see it. You're right. You would think to obey convention, this would be the correct notation, but they don't do that for some reason. They will do it in all other cases. They will put the oxygen is bonded to wherever it's bonded right here would be the correct atom, but I have seen situations like this. But if you see like a long string, basically I will manually remove this one because it's an annoying exception. Wherever, if you have multiple things, so if you have A, B, C, and you have like A, B, I don't want to really C, I'll do X. Wherever's closest to it is what's going to be bonded right there. The other thing I want to do is this. Little diagram. and that. Do y'all remember what these are? This is called a wedge. This is called a solid line. This is called a dashed line. What do you think it means? A wedge just means that it's towards you. A dashed line, and sometimes they space it out like that, means it's away from you. Remember, these are 3D molecules. They exist in three-dimensional space. Where is it? Yeah, amphetamine. Some molecules are, and let me get a pronunciation of this word.
Enantiomers.
Enantiomers. An enantiomer is a chiral molecule. I'm guessing I'm going to have to give you the definition of chiral. Do y'all know what chiral is? Anyone watch Alchemy? Or what's it called? It's an anime. Yeah, Fullmetal Alchemist. Oh, you should watch it. A chiral is your hands. Mirror images of each other. Mirror image is a different molecule. So, because they exist in three-dimensional space, think about your hands. Are they identical? Can you put a left-handed glove on your right hand? Can you rotate your hand around and put it in? No, your right hand is fundamentally different from your left hand. Let me look up an example. So here they're both pointed away from us when we rotate them. If I were to rotate this, if it's pointing away from the paper and I do a 180 degrees, it would be pointing toward us, right? If your thumb was pointing down and you do a 180 flip, it'd be pointing up. But they're still both pointing away from us. These are two totally different chemicals. I will give you the most common example. You might have wondered this yourself at one point. I won't do meth, I'll do amphetamine. Amphetamine! How do you make methamphetamine? Do y'all know? Do you know at least some of the ingredients to go get it? What is the number one thing to go to a drugstore and buy, though? But you should at least know this. These are the decompressants. You know they're restricted. You can't, if you walk in and buy it, if you try to buy like 5 packages of them, your name will be put on a list. I'll just show you. This is the homework. I have a whole bunch of notes for you guys. With it too. So this is amphetamine. One is pointed toward you, one's pointed away. So the left-handedness is called lexomethamphetamine. Oh, and that's not meth. It should be lexoamphetamine. That's going to be a mistake on the thing. I just realized that. The other one is Dex. So you have L. They usually abbreviate it as L. Amphetamine. And D.
If you have seniors in your class, Miss Lee needs you to come by the front office. If you have seniors in your class, Miss Lee needs you to come by the front office. Thank you.
So we have receptors in our body, and you think of it like a hand in the glove. Your receptors are like the glove. Your hand is like a chiral molecule. The left-handed one, the Lexo, or levo, amphetamine, is a nasal decompressant. You have a receptor in your nose and your sinuses that this bonds to. It does nothing whatsoever but nasal decompressant. So allergy medicine will have this in it. The right-handed one is a central nervous system stimulant. It's used to treat ADHD. It bonds with a receptor in your brain. Even though the only difference, again, here you see that CH3 pudding here. Usually they like putting it on these dark lines. Let's go ahead and do the formula for this. So we have basically Ritalin. This one right here is a nasal decompressant. The CH3, whenever you see it, is entirely optional. They just like doing it for these dashed lines. And whenever you see it written like this, note it's not going to be NHH. First of all, H can't bond to an H because that would be 4 atoms around this hydrogen. Hydrogen can only have at most. It'll be like this. You treat this line no differently than this line. This is still a endpoint of a line. It's just in 3-dimensional space. So we have one here, one here, one here, one here, one here, 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 one here, not one there, and one here. So carbon, double bonded with a carbon, single bonded to a carbon, double bonded here. You might also see this ring a lot, or this benzene ring. A lot of organic chemicals have a benzene ring. And you don't have to do this dashed line. I don't care about which molecule you're referring to. Alright, we need to balance all these. 1, 2, 3, 4. Fourth one. Fourth one. 1, 2, 3. Fourth one. 1, 2, 3, 4. That one's good. One right there. 1, 2. So I need 2 lines here. 3. So I need a fourth one here. Only 1. So I need 3 here. And this is my only non-carbon. 1, 2, 3, 4, 5. So these are the original dots that would be around it. That's the original 5 valences. So what is the chemical formula for this? 1, 2, 3, 4, 5, 6, 7, 8, 9. Hydrogen, you always put carbon and hydrogen first, by the way. Carbon and hydrogen are always written first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And 1 nitrogen. So that's amphetamine, the nasal decompressant. So as I said, I don't care if you leave it like this. So this could be dashed, or it could be a wedge. And I don't care if you leave it unflattened and you end up with this shape. Just make sure you put the dots around the oxygen, or you flatten it. Personally, a lot of them look better flattened. This one turned out ugly, but then so this one is kind of ugly. Let's do. And let's do. I don't want to put sodium or anything in there. So what this looks like, I just made it up. How many carbon do we have? We have 3. Again, you can either go and flatten it or not. This is what you would do if it's not flattened. Or if you flatten it, choose one starting point. I have a chlorine attached to a carbon, attached to another carbon, double bond it with a carbon, attached to an oxygen. So all the carbons, you need 4 lines around it. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And make sure you add dots around the other ones. So chlorine, which have 1, 2, 3, 4, 5, 6, 7. These are the original valence electrons. If you count all the electrons around it, you have to remember that it's sharing one, the carbon is sharing one with it. And 1, 2, 3, 4. This wouldn't work. Yeah. One, 2, 3, 4, 5, 6, 7, 8. Oh. That's the trouble about making up a random chemical, is it might not be physically possible. So if you flattened it, so 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 1, 2, 3, 4. This one's good. Has 4 lines around it. 1, 2, 3, 4, 5, 6. So that's what it looked like flattened. Easy, right? I tried to make something easy and trivial. What's a good chemical, organic or meaning carbon? Y'all think of? Glucose. You chose the one that I don't want to get into. It uses a projection. We'll do it, but the wedge shapes are different. So we'll do glucose. This is organic. So glucose has this weird shape. This is known as a, let's see if I can get the name. Yeah, that's the reason why. Is some molecules shape. This is known as the Hayworth projection. It's a way of doing the skeletal structures to make it look more 3D. Some molecules, the shape is, so we have chirality, we have chiral molecules, but we also have, for example, this situation. We can have it bend up, down, and back up, or we can have it bend up, down, and back left. And this is all on the same plane. So I can't use wedges and I can't use arrows up. These molecules are actually bent like that because remember the atoms when we did geometry do it. It makes them bend like this. And so glucose is a chemical where you actually have to know more information on its geometry to actually represent it. As there is a lot of other sugars like it. But in a nutshell, its overall formula is this. Yeah, removing all the extra projections. And I do not give y'all anything this complicated. Technically, this one's pointing straight down. I'll do it over here. This is pointing down too. And that should be OH. So carbon here, carbon here, carbon here, carbon here, carbon here. Technically, there's a carbon here too. Usually what you start out with is figuring out the structure of the chemicals bonded here. What would be the Lewis dot diagram for this? And carbon always goes in the middle. I'm going to look it up to make sure. I think the oxygen goes to it too. Yeah, so it'd be a carbon with an oxygen, and the H will be bonded with the oxygen, and there'll be 2 hydrogen. It's basically what it says. We have CH, so you do it first. This is a carbon with 2 hydrogen attached, and a hydrogen attached to the oxygen, and the oxygen will attach to the carbon because it can't go anywhere else. So it looks like this. You just need to do Lewis dot. So 1, 2, 3, 4. 1, 2, 3, 4. I think that could be it. 1, 2, 3, 4, 5, 6. Oh well. We're out of time. This is what I was going to pass up Monday, because I'm going to be gone Monday. And I guess this is also going to be able to work for Tuesday and Wednesday when you're gone too. We're not running. Have you seen Demon Slayer? Maybe you're sure.